So, yeah.
That's right.
All right. So let me let's just return briefly to
It was going to work, but then I realized I was supposed to discuss it. I'm sorry.
Sprite stuff.
I'm really sorry.
So actually, let me come back just briefly to remind ourselves how characters were defined, right? By basically row and column. Because the same kind of approach is what we'll use for sprites, except they're just bigger. Okay, so but this kind of idea is similar. So just keep that in mind. Okay, so where were we? Sprites. Okay, so 24 by 21, as we said, that's 63 bytes, and uh, each sprite can have one color unless you're in multicolor mode. But that color can be different per sprite, okay, which is kind of nice. Um, you can scale them horizontally, vertically, or both by a factor of 2. And then you can set priorities and do collision stuff. We'll talk about all that later. So the way the Sprite Pointer worked is a Sprite Pointer is just a number from 0 to 255 and points to one of the 64K chunks, or sorry, 64 byte chunks in the VIC2's current memory bank. So remember, there's 64K of RAM that we can address. The VIC2 can only see in sort of essentially 16K of it at a time. So that divides things into 4 banks, 0 through 3. And then the Sprite pointer is a number, basically which 64 byte chunk is the sprite, and then you convert the bank number and the Sprite pointer number to a location with this formula, right? So bank times 16K plus Sprite pointer times 64. And so the sprites will always start on a 64, a multiple of 64 address, which is nice. Okay. Um, okay. So, and we'll look at an example of this in a minute. Yeah, Cole.
Spent a couple days in these sprites that we're talking about, the same thing from like scratch, right? Like little characters.
Yeah, they're just art, right? Or so the when you define one, right, you're defining it with a 63 basically byte grid, and I'll show you guys what the grid sort of looks like here in a minute. Um, and kind of like characters where each element of the like if we draw basically a 24 by 21 grid, okay, then each one of those spaces is a single pixel and could either be a 0 or a 1. 0 would mean it's the background color. 1 would mean it's whatever the color is for the sprite. Yeah.
So this is essentially the ones of Minecraft, like a pork sprite.
Like a what sprite?
A pork sprite, or like a steak, like something, an item. Just you literally just are holding a bunch of pixels. That's all it is.
Pretty much, yeah.
That's what a sprite is.
Yeah, it's just, and so the definition of the sprite is just zeros to indicate that pixel is background, 1 to indicate it's not, and then the color register says what color those ones get replaced with.
So it's when you say 64 by 64 by 64 pixels, right?
No, it's 24 by 21 pixels.
Right. 24 by 21 pixels. Okay, that's how small it is.
Mm-hmm.
That's how small the like as in pixels on like so that cursor right now. How big is that? I'm trying to get like the scale of this thing in my head.
Right. No, good question. This.
Pixels, I'm thinking of the 0 ones like an A. Like how big is the A?
Right. Okay. So a sprite is basically it's going to be basically 3 characters wide.
Okay, so 3 characters wide by how many tall?
Basically just shy of 3.
Okay, so about 3 by 3 in terms of so it's about SEALOA.
Yeah, it would be about. Oops. A sprite is going to be about the size of this square, roughly.
You make it smaller.
You can by basically making a bunch of it background, right? So that's what the sprite is, but that doesn't mean that you have to use the whole space um, for the graphics of it. Okay, we'll look at some examples to kind of to see this. Okay, so there's that. So we talked about the sprite pointers, um, and the sprite colors are set through in these registers D27 through D2E, and uh, basically what you put in each register is a number from 0 to 15, and that corresponds to which of the 16 colors in the C64's color palette you can use. Okay, um, and then sprites can be turned off or on by setting the appropriate bit of D15, bit 0 for sprite 0, and so on. Okay, so what this means is that you can copy all the data and change the sprite and then turn it on, and it's going to appear instantly rather than turning it on and then copying the data, right? That makes more sense to do. Um, and then multicolor mode uses a couple of extra registers. We'll just worry about single color mode for the moment. Okay, you can double the sprites horizontally or vertically, but you can't shrink them. And there's the 2 bits, so you can double horizontally or vertically independently of the others. So you don't have to do both directions. Okay, the positioning is the annoying thing because, well, how wide is the screen in pixels? 320. Okay, that's bigger than 256 or 255, so we can't represent that with a single 8-bit value. So the numbers, the range 0 through 255 are handled like normal. And then if you're beyond that, then there's a ninth bit that gets set, the most significant bit position. So, hang on, Rippy, yeah.
What's the runtime analysis of how this works? Because does it slow down when it extends past the 256 mark? Because I have to do that regard.
Very well. Okay, in basic, you would have to have a conditional that basically said if, like, let's say you're removing a sprite from left to right, you would have to say, okay, the sprite's value, well, okay, in assembly, you'll have to have a conditional. In basic, because basic can handle up to, basic doesn't have any limitation in terms of the type of size of number. Um, you would just have to say, okay, I'll take the x coordinate, which is I'll think of as a mathematical coordinate, and I'll poke the lower 8 bits of it to this place and the upper bit to that place, and using a Boolean operation. We'll see an example of that. Okay, so is it going to slow things down? In basic, if you had all 8 sprites trying to go all at the same time, yeah, it probably would slow down a little bit. In assembly, it's not going to be a problem because that will run so quickly that it's not an issue. However, in assembly, you would have to basically say if the carry bit got set when you added to the least significant bits, then add the carry bit to the appropriate bit of the most significant bit register. Okay, we'll get to that, believe me. So, um, okay, now the the there is a way to do smooth scrolling of backgrounds, which we'll talk about later. But there's also not all, like 0, 0 is not here; it's actually there. Okay, which makes sense, right? But what this means is that you can have your sprites could have come in underneath the background or underneath this border, and it makes it appear that they're continuously sort of scrolling into the image.
Are they loading like new ones in the left? Like zero?
They're just hidden. They're there. It's just you can't see it.
So if you had an actual Commodore, how much of that blue
This light blue border?
Yeah, all of it?
Yeah.
Okay.
Yeah.
So it's
So
just,
this light blue border is real. It's not just the emulator.
so it's a matter of just having the coordinate set to be 0, 0 at the top of the light blue border so that you can load things behind it if
Mhm.
if you draw it on top of it.
Right. Well, it's drawn behind it.
Oh.
Yeah, it's drawn. The sprites are drawn behind the
Yeah,
border,
like
so
the
they would.
border itself is drawn on top of
Right,
the
right.
sprites.
And the border, right, unless you do fancy raster tricks, can only be a single color, which for a game we'd probably set to be black, but we don't have to, right? Yeah. Do you have a question? No, not really. You sort of. I mean, this is one of the limitations of the hardware. Well, okay, so there's two different when I say scrolling, I mean two different things. One would be a sprite can be moving, right, in and out, okay, and appearing to be coming from off screen. So that's sort of one kind of scrolling. The other kind of scrolling is that the background itself could scroll, right? So think like Mario Brothers, where when you move, the background scrolls to give you this perception of depth. You can do that too. Now, is this hardware as advanced as the Mario or as the Nintendo's graphics hardware? No, it's more limited than it in a number of ways. Um, but yeah, it's okay. Okay, so the positions. Um, so each address is going to need an 8 bits for the X, 8 bits for the Y, and then the ninth bit for all of the X positions gets stored in the same byte, and it's 1 bit per sprite. Yeah,
Just an and mask or
right. To get the correct one. Yeah, you'd mask to either read or write the correct one. Okay, so basically, we'll look at an example here. And so, what do we need to do? Well, we have to define the sprite. We've got to write that data into a 64-bit, or sorry, byte segments. That should be byte. We've got to set the pointer, the sprite pointer, to point to that location. We've got to turn on the sprite. We've got to say which color the sprite is, and we've got to make sure that the position is wherever we want it to be. Okay, so as sort of an example, let's load. This is page 153 from the manual. Hi, Shane. Oops, that one's not in there.
wait, don't you want to say load quotation mark page
Oh, yeah,
153
thank
column
you, because I'm an idiot. There we go. Okay, so here's our program. It's pretty simple. Now, the first thing is you see this heart there. You could it's not actually going to print that. That's just the way that character number, I think 133 is displayed. You can get that by hitting Shift and the clear home button, which on the Commodore is, special buttons. But basically, all that's going to do is clear the screen. Okay, so well, it's that particular character if you print it. So I think you could also print car dollar sign of I think it's 133. Don't quote me on that, but it's a yeah, and all that does is clear the screen. Okay, so that we have a blank screen to work with, and then when the program ends, it'll plop the ready down again. Uh, but only once the program ends. Okay, so what are we doing here? Well, we're poking a bunch of stuff. Okay, um, and the first thing is I'm poking address 2040 with 13. Okay, so what is address 2040? Well, is it? Okay. Well, we'll look at that in a minute. Okay. So we need to figure out, well, what is address 2040? So we'll need to look at the memory map for the C64. Okay. Then we also have poking 832 to 832 plus 62. Okay. So 832 plus 62, that's basically 60, 63 bytes worth of stuff, right? So what is that going to do? What this tells me is that 832 is the base address of the actual Sprite data. That's where we're putting the art. Okay, and what is it poking here? It's poking 255 into each of those bytes, and so basically we'll just have a big block. Okay, because it's all ones everywhere. Okay, fine. All right, and then we're poking things starting at 53,248, offset by a couple of different values. Okay, and those guys are basically going to be all the Sprite control registers. Okay, that are going to set, amongst other things, what's our Sprite Pointer, which Sprite are we turning on, what color is it, all of that stuff. Okay, and then 2040 is just what's in 2040 with the number 13. Well, for that, we just, like I said, have to look at the memory map. And so let me open up a web browser here. Okay, what did we say it was? 2040 decimal? Okay. Default area for Sprite pointers. Okay, so the Sprite pointers by default go in these addresses, 2040 to 2047. Okay, and so the first command here has said the Sprite pointer for Sprite 0 is 13. And guess what 13 times 64 is? 832, which is exactly where we start actually putting the Sprite data. Okay, does that make sense? Because remember this, so the Sprite pointer is only a number from 0 to 255. Okay, so by default, and currently here, which bank is the VIC2 given? Which one have we allotted to it? Bank 0. Okay, and therefore, how do we get the memory address for a Sprite located at pointer 13? We do bank times 16K. Well, if the bank is 0, then that's 0, plus the Sprite pointer 13 times 64, because each Sprite is 64K or 64 bytes in size. We're not in page 0. Bank 0 and page 0 are different. So page 0 is the lowest 256 bytes of memory. Bank 0 is the lowest 16K of memory. Okay. Yeah. So page 0 is most of it is spoken for on the Commodore. Okay. And page 0 of memory, like I said, that lowest 256 bytes. So the processor basically only has 3 registers that you can directly work with. And really, in some other senses, only 1. That's not a whole lot of registers, is it? Right? Because how many did we have when we were doing stuff in 64-bit ARM? How many registers? Yeah, it's basically 32. Okay. Now, there were a few of them that had specialized purposes, so we couldn't use them for general stuff. And when we were working under Linux, there were sort of conventions as to how you use some of the registers for parameter passing. But essentially, you had 30 or so. Okay. This processor, one of the things, like in order to fabricate on a processor a register, that takes a lot of transistors. Okay. And you don't want to, like, if you want to keep the processor small and therefore inexpensive to produce, you have to limit how many registers and other memory is there. Okay. And so the designers of the processor did that. It basically only had 3. okay, that kept the processor much more simple and therefore made it easier to fabricate and less expensive and so on and so on. Okay. Now, one of the things they did though was they made it so that memory access to the lowest 256 bytes was faster than all other memory accesses. Okay. And so what that meant is that page 0 of RAM kind of became like an extended bank of registers. They weren't quite as fast as an onboard register, but they were faster than the rest of memory. Okay. Page 1 gets used for the call stack, which we'll talk about when we do the machine code stuff. So you remember when we were doing AR64, right? We had a stack and we had to worry about the stack pointer and pushing things and popping things off of the stack. That's page 1 of memory, just period, right? It can be no bigger than page 1. If you do, you overflow the stack and that's bad. Okay. Okay. Yes? Okay. So 2040 is the sprite pointer, and we're saying that our sprite is in location 13. 13 times 64 is 832, which is the base memory address. So in the 63 bytes, starting with byte 832, we're writing, well, 255 to all of them. Okay, whatever. And then V here, 53248, these addresses here are all of the VIC2 control registers that are down kind of towards the bottom of the memory map. So let's look at the memory map and see what we got. What was it, 53248? What was it? Sorry. 53248, yeah. Okay, plus 21, 39, 24, and so on. Okay, so this is the I/O area. Okay, was it 5? Yeah, 53248. Okay, so D0 hex. And basically this is memory map stuff that we're using. So all of it's I/O and memory map stuff, but the specific stuff we're looking at are, well, what's in 53248? The coordinates of the X coordinates of the sprite, the Y coordinates of the sprite, and then the most significant bit down here, the screen control registers. Okay, and so which ones of these have we used? Let me put this you, yeah, me, yeah, you, yeah. Okay, so what have we done? We've poked that address plus 1. So what is that address plus 1 would be the Y coordinate. So the very bottom line, line 80, pokes the Y coordinate to be what? Y coordinate, not X coordinate. Line 80. Okay, V plus 1. Yeah, so that's setting the Y coordinate to 100. Okay, how do I know it's setting the Y coordinate? Because what is address this plus 1? 53249 is Sprite Zero's Y coordinate, right? Okay, now what's its X coordinate? That's at address 53248. Where's that get set here? Which line? Uh, V is defined to be 53248 on line 40. Okay, so where are we poking 53248 with something? Line 70. That one plus 1, right? Okay. So line 70 is poking address 53248 with what value? 24. Okay. And so the sprite is going to initially be placed at 24x 100y. I don't remember. I will have to look.
Is this going to be half into the border?
Possibly. We'll see. Okay. Um, so, all, is this going to animate the sprite in any way? No. All it's going to do is create a sprite by putting some data in memory. And now we're not finished because what are lines 50 and 60 going to do? Well, all right. So address plus 21, that would be 53269. That had to happen. Okay, what's in address 53269? Okay, we need to, in 53269, we're enabling sprite number 0 by writing a 1 to that byte. Okay, so it puts a 1 in the 0th bit. And, okay, what about plus 39? That would be what, 77? 87? Yes? Okay. And 87, what's there? Sprite 0 color, only, of course, the lower 4 bits of it, because how many colors do you have? 16, and so how many bits do you need to describe that color? Just 4. Okay, so the upper 4 bits are unused. Okay, so we're setting sprite 0 to be color number 1, whatever color number 1 is in our palette. Okay. Now, are we ever in this thing adjusting the position of the sprite? We set it, but we never change it. Okay, we also never change the color. We also never change the sprite pointer. We also never change any of the sprite data. Okay, so what should happen if I run this? Draw a sprite, and that's it. Oh, would help if I put the... Okay, so we have there a Beautimus sprite that is, as Rippy indicated, partially off the screen. A little bit. Well, how can we find that out? Why don't we change the program to... All right, well, so 25 is your... Yeah, okay. So, yes. So the pixel 24, that means that the border is 24 pixels wide. Asterisk is it actually depends on whether or not you've got smooth scrolling mode or on or off. Okay, right now we don't have, so it's off, so we don't have to worry about it. This also varies from NTSC versus PAL machines because the scan lines are different on PAL machines because they're operating at 50 hertz, not 60 hertz. Sorry. So, okay. So, now what is this? What do you notice here? Well, it is kind of big. Well, it's over the text, right? And it's sort of independent from what's going on in terms of the text. Okay. Now, this is a good thing in some sense because if you want to make a game, what are you going to use for your tiles in terms of like your background and stuff? Yeah, it's all going to be stuff that's basically playing the role of characters. Okay, the sprites are independent from that. Because if all you had were 8 sprites and that's it, then you'd be kind of hosed, right? You couldn't do anything like Mario. Okay. Now, that said, there is also there are some collision things that enable and allow us to detect whether or not a collision between sprites or sprites and backgrounds has happened. I don't want to really deal with that right now. But yeah, okay. And the priority register, right? We never wrote to this address. So 53275, let's print. Okay. So what does that mean? In front of the screen content. So what happens if I set this to a 1? Yeah, okay. So if I poke 53275 with a 1, then now the sprite is behind the background or behind the text stuff instead of in front of it.
So, enlighten me. Why is it that it can handle multicolored stuff like that completely fine without having to like screw up like the height and shit? Like seriously, like what is going on here?
Yes, okay. So you're bothered by the fact that
This works beautifully and it's beautiful, like it doesn't have any problems. What is going on here that I'm not seeing? What's the trick? I mean, yes, I very much want to know.
let's meet at Wally's on Thursday and have some drinks and then I can explain it. Yeah. So, okay, like yeah. No, Rippy, your question is good, right? Because you look at this and you say, wait a minute, Dr. McKinney. Last time or last week you said the background could only be one color, and it looks like I have two colors now for a background,
Yes.
right? But it's not that I have two colors for a background. I have one color for a background and one color for a sprite that's layered underneath the text, so it looks like it's a second background color.
Okay.
And the chip was designed to be able to do this. Let's see, background, sprite, characters, and then the sprite, you can layer, you can set priority of who's in charge. So basically just like 2 or 3. Is it limiting? Yes. This is 1982. Okay. Now, later machines, so for example, like I'll use the Nintendo and the Super Nintendo. The Super Nintendo, you could have a lot more layers. Okay. And if you think about some of the games you played on those machines, right, how many background layers you had scrolling and stuff, and their scrolling was all independent from each other, was all how you were able to get the illusion of depth. But we're firmly in the 8-bit era, not the 16-bit era of the.
How difficult would that be to actually implement? Because all you would need is several layers that just have offsets relative to one another. So one would move at a rate of 8, one would move at a rate of like 4, and one would move at a rate of 2.
Well, because the chip can't handle all that. You would the video chip has to be designed to be able to do that. Okay. A. B. Where are all those backgrounds stored in memory? Well, those are bitmaps probably, and you've only got 64K of memory for the entire thing, right? Like there's just eventually just run out of memory is the problem. Okay. Now this is why a couple things would happen on these old machines. They would use a technique called bank switching. So, for example, the Commodore 128 had 128K of memory, but it can only see 64K of it at a time. Okay, and so bank switching, you basically swap in and out different parts of the memory and as you're going. And this would be kind of like a crude analogy would be like, let's say you had a game that needed 2 floppies. Okay, the game would have to stop and say, okay, please insert floppy number 2. And then you'd put it in, and then it would load. Okay, bank switching obviously was a shitload faster than that. But yeah, and NES games did this too, right? So they used on the cartridges things that did memory mapping and bank switching. It's really kind of cool how they were able to do it.
That, the way you just described that, I think now makes me remember the old Game Boy games that when you save, you didn't actually save, you get like a character number thing, and then just swap out and stuff like that. Like you didn't actually save, you just save everything into like a letter combination that would then set all the registers.
Right. Right. It's like a password type thing.
Yeah.
Mega Man was famous for this, right? So, yeah. Okay. So the sprite can be in front or behind the text. Okay. And how did I do that? Well, we did it by setting the priority register 53275. Okay. Right. So, and I can obviously change this back. All right. So let me change it back to a 0. Yes. Mm-hmm. Yeah.
In what way does it prioritize who goes in front?
That I do not remember off the top of my head.
I'm assuming it has something to do with whatever sprite you're on, 0 to 8. So the 8 will
Well,
be
0
the
through
very
7.
front or the very back. Is what I'm guessing.
Yeah, that I do not remember. Okay, but yeah, Sprite Priority is an issue. Okay. Now, for now, I just want to deal with single sprites, so we don't really need to worry about that this moment. But yeah, okay. Okay, so let's well, okay. So there's one way we can do this, right? And kind of answer Rippy's question, right? So this thing turns on Sprite 0 and points it to 832 and then, right? So what about if we also poke 2041 with 13 and we poke, let's see, it'd be 53250 with, let's say 50, and we poke 53251 with 100. Oops. That should be a comma. Because I'm doing all of those. Yeah. Because I was a dumbass. Okay. So I've done those. Okay. I also need to turn on sprite number 1. Okay. And that was in control register 21, was it? Where were my? Okay. So I got my coordinates. Plus 21 was 69. Okay. So I need to poke. I need to poke 53269 with a 2. 53269 with a 2. Okay. Oh, sorry, 3, not 2. Because I want to turn on both sprites 0 and 1.
Bit number X, 1 and 2. Got it. So you just put in bit number 2, 1, 0.
And bit number 1, 0, 1.
So now if you did, say, 5, but you already poached the location of the other, so I don't know where the default location would be.
So I turned off the.
So what would that be? You want, yeah.
Okay.
Well,
but
actually, can you put 2 P5 in here?
Sure.
And where are they?
Ah.
They're behind the screen?
Well, they're behind the screen, but also, well, okay, they're not behind the screen. I haven't set their locations.
Yeah.
Okay, and so right now they're probably 0, 0, so we can't see them.
Yeah.
The second thing is I haven't set the sprite pointers, so they might be pointing to garbage data in memory. Okay. Third thing is I never set the colors. Right? So why is it that this first sprite is white and the second sprite is this sort of brick red color? Well, actually, I never set it to that. Well, I set white to the first one, but where's the color registers? Sprite 0 color was in 53287. Okay, that was poking 39 with the 1. Okay, so what's in Sprite? If I peak location, or print peak, sorry. What was it, 53288? I get 242. Okay, now obviously 242, I don't care about the upper 4 bits. So what are the lower 4 bits? So let me do that. So I would AND this against 7 to get the lower 4 bits. Why didn't that work?
Because you're shoving too much stuff on, let's just, copy what you have there and put it underneath already.
Oh, I think I need a set of parentheses.
You can do 53, 288, and 7.
No, because I want to peek first. Okay, 2. Okay, so 242, the least significant 4 bits are the number 2. Okay, so that's color number 2, not color number 1, or yeah, color number 1. Okay, which is this brick red color. Now, if I poke that location, okay, it's a little hard to see on, oh, well, it's pretty terrible on my monitor. The projector actually makes it look better. Yeah, it's kind of this light green color, right? And of course, there are 16 possible colors. And so I could, for example, do for I equals 0 to 15, poke 53288 with I, next.
Why not?
And so I just cycled through all 16 of them really quickly. Okay, now, and I could also do, I could make a delay loop that slows it down a little bit. Huh? Okay. All right. Well, so let's make a delay loop. Right. But all I was doing was poking to the appropriate thing. Okay. So let's poke that address and switch it back to that red color because that's easier to see. Okay. And then where did I set its coordinates? I set them up here. So so let me set its X coordinate to 30.
So prioritize Sprite 1.
Sprite 0.
Or Sprite 0 as the top, and then Sprite 8 would be the furthest back on the lower top.
Right. Okay. And in fact, let's turn on Sprite number.
We already turned them all on.
Well, we did. Okay, but let's set the pointer. So I need to poke 2042 to be 13. Okay, I need to poke. What is the location of it? So I need. Too far. I need X location. Okay, so let's do 53252 with 40, and let's poke 53253 with 100. Okay. Yeah. All right. What was the address for the background priority setting? What was that one? I went too far. Okay. Priority 53275. Okay, so let's turn poke 53275. Let's poke that. We want, so 0 means foreground, 1 means background. So let me change bit.
So you can have a mix of foreground and background. The other two are drawn up front and that one's drawn behind.
But they're not.
The same priorities.
Yeah. So the sprite priority, right, is that sprite 0 is always drawn on top of another sprite.
So 0, 1, 1,
and so on. Yeah, and which this demonstrates. So for this, we wouldn't be able to tell because right now their sprite data is all ones. But, well, so basically, let me just kind of write this on the chalkboard. The way you set the sprite data, right? So the sprites are The sprites are 24 by 21, right? Pixels. Okay. Now 24 is a group of 3 8-bit things. So the bits that I'm setting in, what was it, address 832, are the first byte worth of stuff. Then the second, then the third. Then I come down to the next row and go through that way. So if you did this in multicolor mode, then what you would have to do is, instead of having 8 bits that are independent, that's 6, 7, 8, what you would have is 4 2-bit chunks that could either be 0, 0, which would mean background, 1, 0, 1, 1, or 0, 1. And then you would have to set the multicolor registers to say what those extra colors were out of the palette. So you would cut down the horizontal resolution because each pixel would be double wide, but still single tall. Yeah. Now, if you combine this, right, like you could do, well, yeah, and then of course you can stretch them as you see fit. You can double the entire sprite width or the sprite height or both. And that's, of course, independent of whether or not you're in multicolor mode. Okay.
But if you doubled the sprite width, that'd be the equivalent of like offsetting how much you lost.
No.
I mean, obviously we get bigger, but like the original resolution, it'd basically be like the original resolution just stretched.
Yeah. So what would be a 2-pixel double wide would turn into a 4-pixel double wide, but all 4 pixels would be the same. That's the trade-off that you have here, right? Now, the Nintendo sort of worked similar to this, except that sprite definitions took up more space because each sprite could have up to 4 colors, 1 background and 3 foreground, and but it wasn't limited to this sort of double wide thing. And you could have a lot more. The Nintendo was capable of producing more than 16 colors, and each sprite could use basically a palette of 4 colors. So you had a lot more ability to do stuff with the NES, but it also was a much more sophisticated graphics chip. So yeah, okay, good. All right, so let's look at some more. So unless you are in scrolling mode, which we'll deal with later, the coordinates of this position here, the top left, is x equals 24, y equals 50. Okay. And it looks, I think, a little bit, that to some extent doesn't quite look right here in the emulator. But if we were doing this on a real machine with real, aspect ratios not getting skewed, then it would look right. So the emulator window here, right? If I stretch this thing, for example, right, it doesn't quite look right. So I guess what I'm saying is that it really look like it looks like that coordinate should be the same in the x and the y direction, but it's 23x50y, or sorry, 24x50y, which doesn't look right. But part of this is we're on an emulator, and so the aspect ratios look a little off. That's just, yeah. But anyway, okay. So let me let's see. So the Sprite Priority business. Let me look at. Let's see. it's not there. That's annoying. All right, hold on. Well, actually, we just did that, so that's okay. Okay, so let me load here. Okay, this one's a little long because it's got a whole bunch of data statements to read out of. Okay, now this is the example from page 167 in the manual. Why did I load page 167B and not just page 167? Because there's some typos, okay, in the original. So I fixed the typos, and basically the typos were pretty simple. It was it was all in the data section. There were missing commas in a few places, and another place where they had an extraneous comma, and so you had illegal values. But that's essentially all I did was fix the data statements. It was pretty obvious what the problems were. Okay, so let me run this one, and we'll talk about it. That's just activating the registers to, like, the same as what we did with music. It's just it's not keeping it on.
Yeah, but I want to know what sound
That whatever. It's not like they have a WAV file that they've imported.
No, I mean, like, what were the registers touching? Like, what waveforms they use?
Well, I mean, let's look at the code, right?
Well, actually, no, I don't want to get off topic. Let's
Well, okay. So what were we basically doing there, right? To make our mouse animate. Okay. So let me open up Atom because I've got that code loaded. Okay, and let me change this to something that's a little bit more readable. Okay, so right, the data lines down at the bottom we can ignore, right? It's just data. Okay, so what is it doing here basically? What is line 5 setting? Address 54272. Yeah, those were, I think, the sound registers. Okay, so we got some sound stuff set up. And then, okay, so notice how they've defined here S and V as basically being the base addresses of the video control registers and the sound control registers. That's why they're called S and V, right? Okay, so the first two lines are basically doing sound stuff, okay? And we'd have to look through the memory map to remind ourselves as to what each of those addresses were, but it's all sound control, okay? And then line 15 is where we start the video stuff. Okay, so what are we doing here? Video, the base address is 53248, okay? And we're poking V plus 21 with number 1. That should be turning on sprite number 1, or sprite number 0, right? Bit 1, okay? And you see where it says print, quote, bracket, clear, whatever? If we were to tokenize this and throw it into on the Commodore, that's what appeared like that heart in the little background. So when you detokenize something, obviously Atom can't print the little heart symbol, and so it sort of does this into a control code. So I guess you got something to add to your tokenizer.
No,
Done. Yeah. Okay. Right. And so that's how you can get the control and color and some of the stuff like that. That are these weird characters. Okay, but anyway, all it does is clear the screen. Okay, 53269, which is V plus 21, right? What was 53269? That was the Sprite control register, right? Which one's on or off? And we turned off all of them except Sprite 0. We only need one Sprite in this case. Okay, then what's going on from 12.288 to all of that stuff? What's going on there?
I'm assuming it's populating information, Sprite.
Yeah, okay. So we're basically putting someplace in memory, right? We've got to put all this data, okay? And the data is just defining the sprites, or, in this case, we've got basically 3 images worth, right? Because we've got 3 frames, if you will, in our animation. Okay. Now, the other thing this makes sense is from 288 to 350, how many bytes is that? 63. And then where's the 64th byte? It would be 12351, which is missing. No, it's not. It's just the omitted one. Because how many bytes do you need for a sprite to be defined? You need 63, but every sprite has to start on a multiple of 64. Okay, so there's a wasted byte. Okay, there's a wasted byte. Sorry. C'est la vie. Okay. Okay, so we've got basically 3 ranges of sprites. Okay. This range, and this range, each 63 bytes. Okay, and those are basically going to be the 3 frames of our mouse animation. Okay, and in this case, they're being written to these 3 blocks of memory. Okay, wherever those are. Great. Okay, but what do the Sprite pointers need to be? Or Sprite Pointer, singular. Okay, so what is V plus 39 and V plus 1? Let's look at those. Okay, what is V plus 1? So what was the base address here? 53248 and 249. What were 53248 and 249? Yeah, the X and Y coordinates of Sprite 0. Okay, so where does this Sprite start? Its initial Y coordinate is at 68. Did we ever set its initial X coordinate? No, because it looks like we're going to do that in our loop so that it'll move across the screen. Okay, that's fine. Okay, and then what about plus 39? So where's that? That'd be 53287. Did I do that right? That's the color for Sprite 0. Okay, and what did we set that to be? It looked like white. It was number 15, whatever color that is. Okay. We'll have to look at the color palette to determine that. Okay. Yeah. It looked white. Maybe it was kind of a grayish, which makes sense. It's a mouse, right? Okay. Good. All right. Then what? We print on at a particular spot. I am a dancing mouse. Okay. Great. We set P to be 192. Okay. We'll see what that does in a minute. For x equals 0 to 347, step 3, okay, this is basically going to be the x position, okay? Now, to your question earlier, Rippy, about the 2, how do you set the 2 bytes? You set them like this, okay? Because, so the x coordinate in a mathematical sense can be 0 up through whatever, right? Theoretically, we could go up to 512 or 511, okay? But what do? We take the high bit is going to be that thing divided by 256 integerized, okay? And the low bit is going to be the remainder of that, okay? So if I have, for example, a number, let's just take as example 300. What's 300 divided by 256? 1 with remainder something or other, okay? So if it's a 1, that means I'm going to write a 1 to the most significant bit register in the appropriate bit position, which in this case is the 0th bit, okay? And then the remainder, whatever that is the lower significant 8 bits.
I don't know what they're saying in music. Like, I don't know where the... Is that the P equals 192? Is that where it's the remainder and then just doing the go sub to 200? Is that where that's where the music has to be?
Yeah, we'll have to go down. We'll have to go down to go sub 200 and 300 and see what they're doing down there. Okay, right. So okay, great. And basically, then not only are they doing this go sub thing, but they're basically making P alternate between 192 and 193. So that's probably how they're getting it to go two different sounds. If it's 192, go make one sound. If it's 193, make the other sound. And then this one just toggles it back and forth. Okay, fine. And then we've got this delay loop here in line 80 for t equals 1 to 60 next. Basically a loop doing nothing. That's going to introduce a delay. So if I change that, it'll go much faster. Okay. And then we're poking 2040 with P. Well, what was 2040? We used that one already. $2040 was the Sprite Pointer location. Okay, so we're poking 2040 with either 192 or 193. Okay, that's good where the 2 sprites are. I thought there would be 3, but I guess.
No, it says P equals P plus 1. If P is greater than 194, says 192, so it was 192, 193, 194.
Oh, 195. Yes. Okay. So there are 3. Yeah. Okay. Good. So yeah. Okay. So now let's just do the arithmetic here. What's 192 times 64? Well, we got a room full of freaking computers. Let's use them. Damn it.
It's 12,280.
Huh? Wasn't that number familiar? Yes, that's the first memory location where our sprite is, right? Hey, look, our sprite pointer actually is pointing correctly. Funny that, right? Okay, and then while we're on the subject, what about if we multiplied by 193 instead of 192? We'd get 12,352, and then 12,416. Okay, so the sprite pointers are actually pointing to where they should be. That makes sense. Okay, good. All right, so the y-coordinate stays fixed in this particular example, and the x-coordinates are changing, right? So what is location V? That's the lower 8 bits. What is location V plus 16? That's the high bit, which in this case, we're only setting it for a single sprite. Otherwise, we need to put like an and or something there, but to mask it. Okay, and then, well, we got something going on here at line 70 and 75 with this go sub business, okay, which is probably the audio control. So let's go down there and see what's happening. And yes, in fact, it is, because what are we doing? We're poking some of the sound registers with some numbers. And that's how we're getting the click, clack, click, clack.
Very much like if you have one, a very detailed like sound map of the waveforms and how you can create the different waveform superpositions. Because like the Commodore 64 manual, specifically section 4, does not really have a very good detailed explanation.
Yeah.
If you found a website that use a better explanation?
Yeah. Well, what's the one that I'm on over here in my web browser? Well, no. C64.org, right? Yeah, there's lots of resources out there because, yeah, you're right. The manual is not as in depth in certain places as you might wish it were, but c'est la vie. So, okay, so lines 200 and 300 are just doing the sound control. And we have 3 different sprite pointers that we're using, and the program is recycling them to determine which sounds to play. So if the sprite pointer is 194, we don't play a sound. And that makes sense, right? Because when we ran this, what did we get? Clack, clack, nothing, clack, clack, nothing, clack, clack, nothing. And so every third frame of our animation, we weren't playing a sound, okay? So you see how it's recycled the sprite pointer to serve as a second role, which is kind of cool.
So we're going to probably get into this later in far out, so I'm going to ask regardless. How do you get the multi-task on this? Like when you're doing games, because we're clearly using the whole game inside the
Very carefully.
It's going to use interrupts, but how do we use interrupts?
Very carefully.
Do we have to program like an interrupt table?
Kind of.
Does it have an interrupt table map?
Sort of. It's not as extensive as what you had with in terms of how many different interrupts you basically there's only 2 kinds of interrupts.
The interrupt table from operating system at the end of the floppies.
Yeah. Yeah. So yes, there are interrupts, and that's how you have to handle stuff, right?
Do you have to program the pit?
The pit. I'm sorry.
Programmable interval timer, like the thing that actually runs the thing and runs the interrupts.
Sort of. So there are 2 kinds of interrupts that this thing can do. One of which is called a non-maskable interrupt, and you can do interrupts that are generated by the raster control. Okay, meaning the scan lines. And yes, but you basically have to write an interrupt handler. Okay. Which we'll get to. Right, because as you can imagine, if you guys have no idea what an interrupt is, cry or drop the class now. No, I'm kidding. It's going to be.
I don't get my diploma if I drop this class. So.
Oh, that's.
Woe unto you. So yes, no interrupts. It's complicated, and that is best dealt with when we get into machine code. So, which is where we're going to transition next, right? So there are some of the things that we really haven't talked about yet with the graphics control, for example, scrolling and a few other things. And some of this stuff I kind of want to come back to after we've kind of gotten the, because I don't want to try and do too much at once with the assembly code, right? Because you've got a new instruction set to learn, right? And then we have to also remember, okay, all of these memory addresses are still there. Okay, so the way I'm going to do this is, and we'll see how this works, we're going to kind of step away from the Commodore for a little bit, at least in terms of the assembly. We'll come back to it later. Okay, and what we're going to do is build 6502 computers on breadboards, and actually wire them up. Now, they're going to be significantly simpler than what the Commodore has, okay? That in terms of, it has a chip, it has some memory, it has a display, which is like a little segment thing, right? And some buttons, but very, very much basic in terms of its hardware capability. Okay, what that means is all of these special registers and addresses that we're having to keep track of, most of them won't exist in our breadboard scenario, okay? But the breadboard thing will require a little bit of extra software, because the way that you'll read and write data to it is we'll be using Raspberries and Arduinos, okay, along with EEPROMs, which are basically programmable chips. And so, yeah, it to some extent, it's going to be for a little bit now for something completely different. And then we'll get back to the Commodore later. Okay. Yeah, now I have to say I'm a little nervous about this because I'm not sure how long the breadboard parts what this is going to take, but we'll find out. Okay. Huh? Oh, you're going to be learning, my friend. So, yeah. Okay. Yes. Yeah. What about assignment 5? How's that sheet music coming?
I'm going to start by a question. They're repeats. Are we just doing one time through?
Right. Okay, good point. So, and this is something I forgot to mention.
We should just do one time through.
Yes.
It's a fair amount of work for everybody.
Well,
We don't have to.
but the repeats are just copy paste, right? So there's that, right? So you guys know how the song goes, right? Where it goes through, you do the chorus, then you do the next thing, then right? There's repeats in it. For the sake of the program, don't worry about that, right? Just put in your stuff, and because the repeats, like I said, are just going to be, from our perspective, either a loop construction or a copy and paste. Okay. But like I said, don't worry about that. Okay. So just literally program what you have, and that's that. And I'll sort the rest of it out. Okay. Yeah. Yeah.
Also
Okay.
put something on the book for where do we find it?
Oh, well, the formula that we had, right? Because what was, huh?
It's wrong. The Commodore 64 manual is wrong. All the frequency mappings are wrong. I had to pull out a tuner and map everything myself.
Would you be so kind as to share the formula with everybody so that we can all?
Everything's shifted down by a half step. So
that makes sense. Because
So
it started on A sharp, it should have started on A.
It's all wrong by an entire sharp. So just shift everything up one. So if you see one online,
Just send me the formula, Rippy. Okay.
So we're starting on A, not A sharp, correct?
Was it what everything was, Rippy? Was everything sharp a note or flat a note?
So it was so sharp that it was down one half step. So you have to shift on the actual table, everything's off by like a diagonal. So,
okay. Yeah, all right. Well, send me the formula and then I can share it with everybody. Okay, because like point being, when you do this, what are you doing? You're encoding, like, and in fact, I would do this with an Excel spreadsheet, right? Where you've got note, duration, or sorry, you've got octave, note, and duration, right? Okay, and then there was that formula, right? Which, if you record it as octave, note, and duration, we can change the formula to tune it correctly. And yeah.
It's also very important to like actually calculate that in. Like it's very bad.
Oh no. Like, sorry. Do that in Excel. Right? Okay. Because what do you have to do? You take the octave, the note, and the duration, and then there's the formula that you plug it into to get a single number, right? Okay. That single number is what's going to be in all your data statements for each note. Okay. So just for the transcribing part, just get everything in an Excel spreadsheet for each note, octave, note number, duration. Okay. Do that. And then we can program in the formula. Yeah.
So the other thing is that the C64 manual, the first time I went through it, randomly just has C0, D0, and C.
There's a typo.
Which
yeah.
are all typos to what they should be, and they should be if I remember
like
D sharp
4 or something.
It's D4, D sharp 4, and then C5.
Yeah. So there are some obvious typos in the manual.
Yeah. It's
okay.
Bad.
And also just to be sure, the middle note is C4, right? The middle C.
Yes. C4 is middle C on the keyboard. Right, on a piano.
C4, if you're reading triple clef sheet music in C, is the one that's right below the line. So you have the D, and then you have the one right below the line. And then C5 is the one that's the third bar up.
Yeah.
Right.
And the bass clef is a line above, and then
yeah. Okay, but C4, right, this they were at least consistent with. When they say C4 in the manual, it means the same as C4 in every music class ever.
Yeah.
Okay. So that's good, right? Okay. Now, what Rippy's talking about is that the frequencies are slightly off.
Yeah, so
Okay.
C4 is the same as C#4.
Right. So what this means, though, and this is why I'm saying use an Excel spreadsheet to transcribe your octave, note, and duration values, because then we can change the formula slightly so that the frequencies come out right without you having to retranscribe everything.
Too late.
Hmm? Well,
that's why we have
too
you,
late
so
for
you can
everybody
do it
but Rippy.
for us.
Yeah. Okay. Yeah, because you guys noticed when we played that song, there were a few places where it just didn't quite sound right. Right. That's part of it, but also, well, yeah. Okay. I mean, yeah, we could spend 2 weeks doing nothing but dicking around with old Wabash,
Oh, lovely.
which would be fun, right? But we got other stuff to do. So, all right, we should quit. So.